Good morning. Welcome to new lecture on modulation, and today we will talk about orthogonal modulation schemes. In the last lecture we have concluded with the Shannon's capacity formula, where we have said that essentially if you increase bandwidth you can have more capacity. Of course, it saturates to a value of p and not log 2 e. That means you can increase bandwidth, increase capacity, but it saturates to this value. Then we have seen by doing simple arithmetic that for a given SNR you need to have apno larger than this expression. So, to have bit error rates arbitrarily small, apno should be larger than SNR divided by log 2 1 plus SNR, and this allows us to trade off bandwidth with apno. So, you can have large bandwidth which reduces the signal to noise ratio, which reduces the apno requirement, but it also reduces the spectral efficiency, and these kind of modulation schemes or this idea is really useful for power constrained channels where the power is the primary resource. Or you can have small bandwidth which increases your signal to noise ratio, which increases the apno requirements and which gives you a good spectral efficiency, and this is really the case in modulation schemes like AMCOM. You are trading off the apno with spectral efficiency. And there we have said that for power constrained channels, orthogonal modulation schemes are really useful. These are capacity reaching modulation schemes, and if you allow to have infinite bandwidth, you can reduce the apno to as small as minus 1.59 dB. So, we will start with orthogonal modulation in this lecture. So, if we have a set of m passband real waveforms, passband waveforms are usually real waveforms, baseband waveforms can be complex for analytical ease, otherwise baseband waveforms are also real waveforms, but we can think about the I and Q component together and we make it complex. But in general, if we have a passband waveform, it has to be a real waveform, and if we have m passband waveforms as MPT, P represents that this is a passband waveform where m takes in value 0 up to m minus 1, such that if I take the inner product of the waveforms from the set, then their inner product is 0, then we know that these passband waveforms are orthogonal waveforms, right. How do we define orthogonality? We define orthogonality by taking the inner product of two waveforms. If the inner product of the two waveforms is 0, then we say that these waveforms are orthogonal waveforms. Okay. So, in orthogonal modulation schemes, we take a set of m waveforms, and these waveforms are orthogonal with respect to each other. Moreover, if you take these waveforms and if we take the shifted version of these waveforms, if you take their inner product, it must also be 0. This we have seen why that this should be 0 for avoiding intersymbol interference. Okay. And if L is 0, that means they are not shifted, then this should give me energy of the symbols if m is n, and if m is not n, then this should be 0. So, this is just saying that these waveforms should be orthogonal. So, if I look at this, I am just considering that these should be orthogonal. If these should be orthogonal, then if m is same as n, then we should get the energy corresponding to each signal, but if the signals are not same signals, if they are different signal, then their inner product should be 0. Okay. So, this should also be 0 only when m is not same as n. If m is same as n, then you are taking the inner product of the signal with itself, and then it should be the energy of the signal. This we have seen in great detail earlier. Okay. So, let me define orthogonal modulation schemes again. So, for orthogonal modulation schemes, I am using m waveforms, and these waveforms are orthogonal to each other. Okay. Again, I can use the same ideas. I can consider a block of b bit, and I can form 2 to the power b symbols, where this 2 to the power b represents the number of symbols for which we are using m. So, if we want to consider the baseband transmitted signal, so in every symbol duration you are sending one of the symbol, right. SMT is the complex baseband representation of the passband signal, as MPT. So, if I have a passband signal, I can also derive its complex baseband representation. So, in one of the symbol duration, you are transmitting SMT, all right, and the CT is the baseband transmitted signal. So, this is what happens in orthogonal modulation scheme, and there are various examples of orthogonal modulation scheme. Basically, you can make these waveforms orthogonal either in frequency domain or in time domain or by doing orthogonal coding, and this we will see. So, the first example of these orthogonal modulation schemes that we will see is frequency shift keying. Okay. So, here what we are talking about are these baseband signals. Okay. We will focus on the baseband signals. So, let us consider the set of baseband signals, and the set of baseband signals are obtained by changing the frequencies of these baseband signals, and of course, these baseband signals have the duration of capital T. So, this is an indicator function, that means that you are truncating this signal in the duration of 0 to t. That means, this signal only spans between 0 to t, outside this duration it is 0. So, this is the set of baseband waveforms that we are using in frequency shift keying. These baseband waveforms only differs in the frequency, right, and hence the name frequency shift keying. Of course, I will take in a value 0 to m minus 1. And of course, because these signals are time limited signals, that means they span only from 0 to t. If you take a signal and you shift a signal with t, then the product of this signal will be 0, because these signals will be non overlapping signals in time. So, what we are saying is, if I have a signal which is limited to duration of t, if I shift this by t, so this will span from t to 2t, then if I multiply this, I will get a 0, because there is no overlap in time domain. So, every time limited signal would satisfy this property. So, we do not have to worry about this condition. So, when L is not 0, this will always be satisfied if I have a time limited signal. Then the inner product of SIT and SJT is simply obtained by multiplying SIT, which is this, with conjugate of SJT, which is this, and this indicator function has been absorbed in the limits. Okay. So, basically I get this expression. So, this is how we calculate the inner product of these two signals, and we want to choose the difference between the two frequencies of these baseband waveforms in such a way that SIPT and SJPT are orthogonal. So, SIPT is the passband equivalent of this baseband signal, SJPT is the passband equivalent of this signal. We want to choose the difference between these frequencies in such a way that their passband equivalent signals are orthogonal. This is what we want. We want the signals to be orthogonal in passband domain. And why we have a mod in here? Because it simply does not matter whether you have a positive or negative, this integration will give you the same value. So, let me define FD as mod of Fi minus Fj. So, what we are saying is, usually it is important to select this FD, which is the minimum frequency which makes SIPT and SJPT orthogonal. And when you do that, you get to a modulation scheme which is known as minimum frequency shift keying, or simply minimum shift keying, which is also abbreviated as MSK. So, what is MSK? MSK is the frequency shift keying in which you are using the frequency of the baseband waveform in such a way that the difference in these frequencies make their passband equivalent signals orthogonal, and at the same time the difference in their frequencies is minimum. Okay. So, you use minimum possible value for Ft. So, to understand this issue, let us recall what we have learned in lecture 19 to 21. In those lectures we have seen that if we have a complex baseband signal, ut is a complex baseband signal, this complex baseband signal can be understood in terms of cosine part and sine part of a signal. So, ut is a complex baseband signal, similarly Vt is a complex baseband signal. Once you have these complex baseband signal, you can also derive their equivalent passband signals. So, upt and vpt are the passband signals. So, in those lectures we have also seen that if you want to calculate the inner product of the passband signals, this inner product is same as the real part of inner product of the baseband signals. This is an important idea that we developed in those lectures and we will use it. So, inner product of two passband signals is same as real part of inner product of complex baseband signals. Using this idea, let us develop the condition for orthogonality of coherent Fsk systems. So, we have said in coherent Fsk systems we want the inner product of the two passband signals to be 0. From this we can think about this equation which says that because inner product of two passband signals is same as real part of inner product of the two baseband signals. So, we can also identify the condition for orthogonality, that is the real part of inner product of two baseband signals should be 0. And we have already seen what is the inner product of these two baseband signals, namely SIT and SJT. So, inner product of these two signals is this. So, what we want is real part of this function should be 0. Now, real part of integration is same as integration of real part. So, from this equation we can easily derive this equation. Okay. Now, what is the real part of complex exponential? It is a cost function. So, from here we can arrive at this equation which says that this function should be 0. Now, if we integrate cos, we get sine. Putting in this limits of integration, we get to the condition that this function should be 0. And we know that sine m pi is 0. So, from this we get that this argument of sine, namely 2 pi fi minus fj times t should be m pi. From here we can say that mod of this difference should be same as m by 2t. So, we can cancel pi by pi and we can shift 2t to this side. Now, for minimum difference in this frequency separation, I can choose m as 1 and I can get that minimum difference in the frequency separations mod should be same as 1 by 2t. So, this is the condition that we have got for establishing the minimum frequency separation that is required to have orthogonality in coherent Fsk systems. Okay. So, this condition corresponds also to minimum bandwidth requirement and it also corresponds to a special kind of frequency shift keying which is known as minimum frequency shift keying, or it is often abbreviated as MSK. So, MSK is a kind of a frequency shift keying which uses this frequency separation between baseband signals. Now, let us see what happens when we have something different, when we have non-coherent frequency shift keying. Once we want to talk about the non-coherent Fsk, the condition of orthogonality is slightly different. Okay. So, what is the difference between coherent and non-coherent? This will become clear now. So, when we are talking about the non-coherent systems, you cannot assume that the two passband signals have the complex exponential at the same frequency. because if you assume that the two passband signals have the complex exponential at the same frequency, inherently what we assume is that the receiver has the same frequency generation as used at the transmitter, and this requires synchronization and other things. In non-coherent systems, we assume that this rotating complex exponential is offset by theta with respect to the rotating complex exponential that is used at the transmitter. And we have also seen in one of the lecture, possibly lecture 21, how to get rid of this theta. Okay. Anyways, at this point what we are assuming is that we are having two passband signals, but the phase of one passband signal is offset with the phase of the another passband signal. If I want to take the inner product of these two signals, the inner product can be simply obtained by taking the real part of inner product of the baseband signal, but now the baseband signal is not V t, the baseband signal is V t times e to the power j theta t. So, this inner product would be same as real part of inner product of these two functions. Now, if you want the orthogonality of these passband signals, you want this to be 0. So, you want this to be 0. So, when this e to the power j theta t pulls out of the inner product, it will come with a conjugation, because inner product operation satisfies Hermitian bilinearity. Okay. This we have seen. Now, for orthogonality, we want this to be 0, and this will be 0 for all values of theta only if inner product of u t with v t is 0. Only if this is 0, then only this quantity, the real part of this thing, will be 0 for all values of theta, and thus the condition of orthogonality for non-coherent Fsk, in which we assume that receiver does not have the complete information about the frequency of the transmitter, where we assume that there is some frequency and phase offset at the carrier used at the receiver with respect to the carrier used at the transmitter. The condition of orthogonality is that the inner product of two baseband signals should be 0. The condition of orthogonality for coherent Fsk, on the other hand, was that the real part of the inner product of the baseband signals should be 0. So, these two conditions are different, and thus you would get a different answer. So, once you want that inner product of baseband signals to be 0, what we want is this should be 0, and this integration evaluates to this. So, it simply means that from this condition we can get that the mod of f I minus f j for minimum value of this quantity is nothing but 1 by t. So, in summary, we have seen that mod of the difference between the two frequencies in case of coherent Fsk should be 1 by 2 t, whereas mod of difference between the two frequencies in case of non-coherent Fsk is 1 by t, because the orthogonality conditions are different. Okay. So, now as we have done for COM, we would be calculating the bandwidth requirement and we would be estimating the spectral efficiency in these modulation schemes. So, we are using AM symbols, and each symbol is separated by a frequency of 1 by 2 t. So, bandwidth requirement in case of coherent Fsk is m times 1 by 2 t. Bit rate, on the other hand, is log to m. So, this is the number of bits times the symbol rate, and symbol rate is 1 by t. So, bit rate is log to m times 1 by t. From this, spectral efficiency can simply be obtained as bit rate divided by the occupied bandwidth. So, you have to divide this thing with m by 2 t, which is the bandwidth required, and for coherent Fsk, the spectral efficiency that we get is 2 log to m by m, and again the units are in bits per second per hertz. Also, let us do it alternatively in a different way, the same thing. So, we know that bandwidth in coherent FSK is m by 2 t. From this we get bandwidth time product or time bandwidth product is approximately m by 2. Number of bits that we have per symbol is log to m. So, spectral efficiency as we have seen is number of bits divided by number of complex dimensions. Number of complex dimensions is same as time bandwidth product, which is m by 2. So, spectral efficiency is 2 log to m by m. The units is bits per complex dimension or bits per 2 real dimension. All right. Why do we have number of bits as log to m? Because we want to consider how many bits you can transmit in a given time bandwidth product, and the time that we are using is corresponding to one symbol. That means, this time bandwidth product corresponds to one symbol. So, in this time you can transmit only one symbol, and thus in this time bandwidth product the number of bits that you can transmit is log to m. All right. So, number of bits that you can transmit in a given time bandwidth product is log to m, and the time bandwidth product or number of complex dimensions is m by 2. So, we get the same answer, but we are using a different philosophy, so that you also get trained in using these ideas. Little bit more. So, we have said that time bandwidth product is approximately m by 2. That means, the number of complex dimensions is m by 2, and in these many complex dimensions we can fit m signals, right. We are using this FSK scheme to support m signals. So, from this I can get in one complex dimension I can fit 2 signals, and this is very clear. If I have one complex dimension, that means 2 real dimensions, I can support 2 FSK signals. Let us see what happens in case of non-coherent FSK. Non-coherent FSK, the bandwidth is m times the frequency separation between 2 symbols, which is 1 by t. Rate is same as before, log to m by t. So, spectral efficiency is also same as before, just that there is a factor of 2 missing, and because here you have a higher bandwidth requirement, because the frequency separation has to be larger for non-coherent FSK as compared to coherent FSK. All right. So, spectral efficiency in case of non-coherent FSK is log to m by m in bits per second per hertz or in bits per complex dimension, does not matter, and because time bandwidth product is m, you can simply get this. If you take TB, it is approximately m. That means, in m complex dimension we were fitting m signal. In one complex dimension we will be able to fit only one signal, and thus the spectral efficiency of non-coherent FSK reduces compared to coherent FSK, right. So, that is the price that you have to pay by having a receiver which does not synchronize well with the transmitter. Okay. If you look at this spectral efficiency versus m, something strange we see. We see that spectral efficiency in this case reduces with respect to m, and that is strange, because earlier we have seen in case of COM the spectral efficiency improves with m, whereas in this FSK modulation schemes spectral efficiency reduces with m, and as m increases we get to very poor values of the spectral efficiency, because these modulation schemes are not optimized to harness higher spectral efficiency as COM was. These modulation schemes are optimized to improve bit error rate for the same signal energy, and this we will see when we see detection, that these modulation schemes have a very low levels of signal energy requirement. But at this point in modulation we are just focusing on the spectral efficiency, and clearly FSK based modulation schemes runs out on the basis of spectral efficiency. So, we have looked into one kind of orthogonal modulation technique, that is frequency shift keying. Then the question comes, are there other ways in which we can construct a set of orthogonal waveforms, and answer is yes. So, to understand that, let us look at this example of pulse position modulation. So, in pulse position modulation, we use pulses, and these pulses are non-overlapping pulses, and if these pulses are non-overlapping, we know that these signals S1t and S2t will be orthogonal signals. So, if you want to multiply these two things, you will get a flat 0. If you get a flat 0, then real part of inner product of these two signals will be 0. Also, the inner product of these two signals will also be 0, because the pulses of these signals are non-overlapping, and this is the main idea behind pulse position modulation. In this case, we are looking at 4 array ppm, that means we have 4 signals. Okay. Now, mathematically we can understand m ppm as a modulation scheme which has signal set like this. So, what we mean by this, to understand that, let us first look back at this waveforms. So, here we can see that this waveform, this pulse is shifted by t by m compared to this pulse. If there are m slots, so if the number of slots is m, and if in each slot I have a pulse, then I can have m ppm system, and thus the difference between any two pulse is t by m. This pulse is shifted by 2 t by m compared to this pulse, and this pulse is shifted by 3 t by m compared to this pulse. That means, in ppm system, each pulse is used in a slot. There are m slots to have m ppm, and the separation between these pulses is I t by m, where I belongs to a set of integers. So, that is what we are saying in that mathematical equation. That means, we have different signals in the signal set, and these signals are arrived by just shifting one pulse by t by m units. So, you can derive different signals by shifting the pulses by different integer multiples of t by m. Here we are saying that the basic pulse is a sync pulse, whereas in the picture we have used the rectangular pulses, of course, because it is easier to draw rectangular pulses, whereas sync pulses are more practical, right, because they have minimum bandwidth requirement. Of course, we could have also used root raised cosine pulses, but for this case we are sticking with sync pulses, and at this moment we are ignoring any issues of intersymbol interference. Okay. So, this I should belong to this set, it can take a value from 0 up to m minus 1. Now, in one of the previous lectures we have derived that T space sync pulses are orthogonal, right. They are not perfectly non-overlapping, but we do not want strictly non-overlapping pulses. What we simply want are the pulses which are orthogonal, and the sync pulses are orthogonal pulses if they are spaced by t units or t by m units, it does not matter. Also remember that though these pulses typically lie in a slot of a duration t by m, but each signal is only transmitted at time instances which are integer multiples of this t. Let us now investigate what is the bit error rate in this m ppm. So, if there are m waveforms, the number of bits would be log to m, and each waveform is transmitted at a time interval of t. So, bit rate, which is number of bits, per time is simply log to m by t. This was also the case in frequency shift keying. The idea is essentially similar. Now, we have seen that bandwidth requirement is typically 1 by 2 t, where t is the pulse duration, and here each pulse duration is t by m, because each pulse essentially is confined to this t by m slot. So, the bandwidth requirement in case of m ppm is approximately m by 2 t. So, from this we can also derive the spectral efficiency, which is bit rate divided by bandwidth, and this will be simply 2 log to m by m. All these things are exactly same as we did in frequency shift keying. So, there are no surprises involved here. If I am interested in time bandwidth product, I can shift this t to this side. So, I can get B t is approximately m by 2, and we know that this time bandwidth product is same as number of complex dimensions. So, in m by 2 complex dimensions, I can fit m signals. That means, in one complex dimension I can fit 2 signals. This is also same as before. So, what we have assumed so far is this is baseband ppm. Now, you can also modulate this ppm at higher frequencies. So, you can convert this baseband ppm into passband ppm, and we know how to go from baseband to passband domain. We can use DSP, double sideband modulation scheme, and let us now see what is the spectral efficiency if we use this double sideband modulation scheme. When you go from baseband to passband, the bandwidth requirement doubles. So, now bandwidth is 2 times m by 2 t, which is m by t. Bit rate remains same, but the spectral efficiency reduces by a factor of 2, and this is similar to non-coherent FSK systems. PPM essentially can be used in non-coherent systems because the inner product of the 2 baseband signals is 0. This is what we require in non-coherent systems. And if you use DSP modulation scheme to go from baseband to passband, then the spectral efficiency that you derive is exactly same as that we derived in the case of non-coherent FSK systems. If for this baseband to passband conversion we use quadrature amplitude modulation scheme, and this case you can think as coherent PPM, because if you are using this quadrature amplitude modulation, essentially we have I and Q components, and to isolate these I and Q components you want a receiver which is synchronous to transmitter. Otherwise, these channels will bleed into each other and the performance will deteriorate. So, what we are assuming is a synchronous receiver, and we assume that this receiver can maintain isolation between I and Q channel. And if I use an M array PPM to independently modulate I and Q channel, my bit rate will simply double, because these channels are independent channel, and then the spectral efficiency would be 2 times the spectral efficiency that we derived in the previous case, where we are just using one channel, and that case will be corresponding to the case of non-coherent PPM, if you want to call it that way, because if we are using just one channel we do not want synchronization. Okay. But if we want to have COM, and if we want to maintain isolation between 2 channels, essentially we are talking about synchronous receivers. So, remember this M denotes the M array PPM that is used to modulate one channel. So, essentially we have considered 2 kinds of orthogonal modulation scheme. We have seen this frequency shift keying, which uses baseband waveforms like this, and we have seen PPM which uses baseband waveforms like this. Of course, for the example that I have shown, PT is sync T, but it does not matter. And if you look carefully, then you see that these modulation schemes use different pulse shapes to transmit a symbol, and these can be thought as examples of nonlinear modulation scheme. Because to transmit one symbol, sometimes I am using a waveform e to the power j 2 pi f1 t, and to transmit another symbol I may be using a different complex exponential. Whereas in linear modulation, the basic pulse remains same and the amplitude of these pulses are altered by this Bn. And you can also obtain the orthogonal waveforms by just manipulating this Bn and keeping these PTs same. And this is the topic of next discussion. So, now we will be focusing on orthogonal modulation schemes which manipulates the symbols to obtain orthogonality between waveforms. The third example of generating these orthogonal waveforms follows from the idea of Walsh-Hadamard codes. These codes are used in the systems like CDMA systems, code division multiplexer systems. CDMA systems have been very popular and used in mobile communication systems as well. So, third generation mobile telecommunication systems used the CDMA codes. Okay. So, before getting into this Walsh-Hadamard codes, let us revise one important idea of this orthogonality. For example, let us take these two baseband waveforms S1t and S2t, and we know this equation, we have used it several times, denoting the linear modulation systems. If I want to take the inner product of this S1t and S2t, I can take this by having this expression here, taking the conjugate of this thing and integrating it. So, what is the inner product? Multiply two signals and integrate, right? Multiply with conjugation if things are complex. Okay. So, this is how we can get to the inner product of S1t and S2t, and the rest is really arithmetic. So, then we know from Fuvini's theorem that I can always arrange these summations. I have arranged these summations like this, and we know that this Pt minus Nt is orthogonal to Pt minus Mt, and this is important to avoid intersymbol interference. We use the idea. So, this pulse should be orthogonal to the pulse which is carrying the mth symbol, this pulse is carrying the nth symbol, and to avoid this intersymbol interference, we know that this should be 0 if m is not same as n, right. And thus what we want is m should be same as n, otherwise this product would be 0. And thus instead of running out this summation for n and m, we can run it only for n, because when m is not same as n, this is going to be 0 and these terms will not contribute to the summation. So, we replace this double summation by single summation running over n, m should be chosen as n, and then we have Bn times Gm conjugate. So, m is same as n, and when n is same as m, we just have Pt minus Nt multiplied by conjugate of Pt minus Nt, and that boils down to the square of mod of Pt minus Nt. Okay. Then I pull out this summation outside this integration and I can get to this expression. If I assume further that this Pt minus Nt are orthonormal waveforms, then I know that this would be 1. That means the energy of these pulses is assumed to be 1. That is what happens in orthonormal case. So, in that case, the inner product of S1t and S2t simply boils down to inner product of Bn with Gn. So, what I am saying is, if you want to consider the orthogonality, and for that orthogonality if you want to force in the inner product of the complex baseband signals to take in some value, you can also do this on the basis of the symbols that you are forming, because inner product of the waveforms is same as the inner product of the symbols that these waveforms have. So, we can work also on this Bn and Gn to make these waveforms orthogonal, and that is the idea behind orthogonal codes. So, we start with this Hadamard matrix, and simple 2 by 2 Hadamard matrix has these elements. So, you can see for this matrix that this is an orthogonal matrix, meaning that the rows are orthogonal and the columns are also orthogonal. How do we test for rows being orthogonal? We have 1 times 1 plus 1 times minus 1. We already know how to compute the inner product of the rows, and this is going to be 0, right. So, the inner product of the rows is 0, inner product of the columns is also 0, and hence this is an orthogonal matrix. So, now if you know this orthogonal matrix, you can construct this S1t by multiplying the first pulse with 1, you can multiply the second pulse which is shifted to t by 2. There are 2 symbols in this waveform, right, or you use 2 pulses for a symbol, however you want to think of it, it is okay. And this pulse is modulated by this one, this pulse is modulated by this one, this pulse is modulated by this minus 1. And hence, because the rows were orthogonal, you can similarly say that these S1t and S2t are also orthogonal, right, because the inner product of S1t and S2t is 0. So, this is what we are saying, that the inner product of S1t and S2t is 0, and hence they can also use in non-coherent systems, right, because this is a more strict condition for orthogonality. The stricter condition for orthogonality is that the inner product of the baseband signals is 0. If inner product of the baseband signals is 0, of course, the real part of inner product of the baseband signals will also be 0, which is more a relaxed condition for orthogonality, which can be used in coherent systems. But because we are using the Walsh code will ensure that the inner product of the baseband signals is also 0, and thus they can be used in non-coherent systems as well. Okay. So, this is for 2 by 2. Can we have more terms in the column? Of course, yes, you can construct nth order Hadamard matrix from n minus 1th order Hadamard matrix by using this simple idea. So, for example, if I have to find W2 from W1, W1 is already obtained. So, this is W1, W1, W1 and minus of W1. So, from W1 you can easily obtain W2 and so on and so forth, you can obtain W3 and W4 and so on and so forth. Okay. So, in this way you can generate these Hadamard matrices of different orders, and once you have this Hadamard matrix, you take different pulses, you generate different baseband signals by modulating the amplitude of these pulses with the elements of the rows of a Hadamard matrix. And this we have already seen that, because here we are making sure that the inner product of S1t and S2t is 0, it can be used in non-coherent systems. For coherent systems, what we can do? We can simply use independent I and Q channels. Okay. We will not be deriving the spectral efficiency and other things for these Walsh codes, because they follow the exact ideas as we developed in PPM and FSK. All the answers that we obtained for FSK and PPM also applies here. They have the same kinds of spectral efficiency and bandwidth requirement. So, in summary, we have discussed 3 kinds of orthogonal modulation schemes. We have seen FSK, PPM and CDMA. All these are examples of orthogonal modulation schemes, and all these systems can be analyzed using the same framework. So, you do not have to use different frameworks for PPM and CDMA. Essentially, they have the same structure, same properties and the same ideas. and once we do detection, we will see again the error performance of all these modulation schemes follows the same trend, and they are also similar. These modulation schemes differ in the implementation methods. Okay, so that is conclude our discussion on orthogonal modulation schemes, but we will like to stretch this little bit further and let us try to see can we construct other interesting signal sets from this orthogonal signal sets. Okay. So, let us see the simple case for orthogonal modulation schemes. Let us say that we are using binary frequency shift keying. So, we have two orthogonal bases and we are transmitting a signal on this orthogonal basis and one signal on this orthogonal basis. These signals are orthogonal to each other. So, from this orthogonal signal set, we can construct what is known as bi-orthogonal signal set. Bi-orthogonal signal set is simply the orthogonal signal set plus the negative of this orthogonal signal set. That means, if I am using a symbol, I also use a symbol which has a negative amplitude than this symbol. So, in orthogonal signal set, only these two symbols will be present. In bi-orthogonal, what I do is I produce the negative replicas of these signals. So, I have this signal and this signal in addition with the two signals that I had before. So, this signal set is known as bi-orthogonal signal set. What about the energy per symbol? Energy per symbol will be same as the energy per symbol here, right, because these symbols are exactly at the same distance, right. So, average energy per symbol will not change. We will see later that probability of error in bi-orthogonal signal set is approximately twice in orthogonal signal set, and that is why it is not used, right. So, this does not perform well with respect to probability of error. But what it does is it improves the spectral efficiency, because here as you can see in one complex dimension we are packing two orthogonal signals, whereas in the case of bi-orthogonal in one complex dimension we can pack 4 signals. Okay. Let us now look at this spectral efficiency of bi-orthogonal codes. So, first let us see that these bi-orthogonal codes are example of coherent signaling system, because if I am using a signal S1t, I am also using a signal minus S1t, and thus I need a system which can detect the phase, and thus I need a coherent system. And we have seen earlier that in coherent system, in m by 2 complex dimensions you can pack m signals. So, spectral efficiency is number of bits which is log to m divided by number of complex dimensions. Number of complex dimensions is m by 2. So, spectral efficiency in case of coherent Fsk systems is 2 by m times log to m. In bi-orthogonal systems, what changes is the number of symbols grows by a factor of 2. Thus, now the spectral efficiency becomes log to 2m, because number of symbols have grown from m to 2m, but the number of complex dimensions have remained same. So, this is the spectral efficiency of bi-orthogonal codes. So, if you want to compare this with this, you can also write this as so. Now, you see that the spectral efficiency improves by this factor 2 by m. So, if m is pretty large, then there is not much saving. So, the spectral efficiency of bi-orthogonal signal set is large compared to orthogonal signal set. So, in orthogonal we know that in one complex dimension we can pack 2 signals. So, in d complex dimension we can pack 2d signals. In bi-orthogonal in d complex dimensions you can pack 4d signals. Another signal set that can be derived from orthogonal signal set is a simplex signal set. So, we had these orthogonal signal set and the simplex signal set can be obtained from this by subtracting from this signal set the mean of signals. So, QMT represents the simplex signal, SMT are orthogonal signals. So, if you subtract from these orthogonal signals the mean of this signal set, you get to simplex signal set. Let us see this with one example. So, in this case we had two orthogonal signals. One orthogonal signal is 1 0, other orthogonal signal is present at 0 1. What is the mean? So, mean is you add these two things, you add these two vectors, you get to this vector and divide by the number of vectors, which is 2. So, this is what the mean is. Now, to get a simplex signal, you take in an orthogonal signal and subtract the mean and you get a simplex signal, half and minus half. So, one simplex signal here. Similarly, from another orthogonal signal, you subtract the mean and you get another simplex signal. So, what you are doing in this process is, this signal has a mean, let us say somewhere here, and you are subtracting the mean. So, you get this signal which has got a mean of 0. And this is important, this is why you obtain the simplex signals. In simplex signals, what you want to do is you want to have a mean of 0. And why is this important? What is the key motivation for simplex signal set? We know that energy in general is energy in fluctuations plus energy in mean, right. So, we have done a similar expression in the case of random variables, where we have seen this expression. So, this is the energy in the mean, this is the energy in the fluctuations, and the total energy is energy in fluctuations plus energy in mean, or the total power is AC power plus DC power. And because what we are doing in simplex signal set, we are making the mean to be 0, we are reducing the signal energy. When we are reducing the symbol energy, the error performance remains same. Why does it remain same? Because error performance just depends upon the distance between the two signals. We are not changing the distance between the two signals. These signals were here, we are just shifting them down. So, we are changing the mean without changing the distance between the two symbols, and thus the error performance does not change when you go from orthogonal signal set to simplex signal set. And so, we are having the best of two worlds. We have been able to reduce the average symbol energy, and we have not sacrificed anything on error performance, and that is why simplex signal sets are good. However, the problem comes in the ease of implementation. So, certain things becomes easier when you have a mean, for example, clock recovery and synchronization in general becomes easier when you have certain mean, and that is why from implementation point of view orthogonal signals were used. But now, because implementation is no cost, simplex signals are also becoming more and more important. Okay. Let us finish this lecture by just looking at two properties of simplex signals. The first property is finding out the energy of simplex signal set if we know the energy of orthogonal signal set. Whenever we are saying energy or power, we always mean that we are talking about the average energy or average power. So, EQ, energy in a simplex signal set, can be obtained by carrying out this integration. QMT we have seen is SMT minus the mean of the orthogonal signal set, and from this we can obtain this mod square of this quantity by having this quantity multiplied with the conjugate of this quantity. This you know that mod square is nothing but x into x conjugate. So, from this we can get this, and now we can multiply term by term. So, we can multiply this SMT with SMT conjugate, and in the end we will have 4 terms. So, this with this, this with this with this, and this with this. So, you multiply term by term, you have 4 terms, and finally by working out the arithmetic, there are no concepts involved, it is just some simple arithmetic operations that you have to do, you can easily obtain the average energy of the simplex signal given by this. So, as m increases, this 1 by m reduces, and thus there is not much gain when you are using simplex signals. If m is small, of course, there is a little bit more gain compared to the orthogonal signals, and thus for large values of m, it does not matter in terms of energy requirement whether you are using simplex signals or orthogonal signals. The next property that we want to prove for simplex signals is that these simplex signals are not orthogonal. In fact, if you take the inner product of 2 simplex signals, you can easily show that this inner product corresponds to minus Es by m, and the proof is trivial, it is simple, it is on the same lines as we did for the first property. So, you can simply expand this QMT. So, this is QMT, and you can write in for this QNT conjugate, which is this. So, now you multiply this term with these 2 terms and this term with these 2 terms, you end up with these 4 terms. So, you have SMT multiplied by SNT conjugate, and then you have to carry out this integration. Then you have this multiplied by this, you get this. Similarly, you have to multiply this with this and you get this term, and finally, you have to multiply this with this and you get this term. You can easily see that this integration will boil down to 0 because SMT and SNT are orthogonal signals. So, this will be 0. Now, when you multiply this SNT with this summation, so the only non-trivial term which will have some effect is when SNT conjugate multiplies with SNT, because all other products will contribute to 0 because SNT will be orthogonal to all other signals, and thus finally you can show that if you multiply this SMT with SNT conjugate, so what we will have is just SNT with SNT conjugate dt, because when SNT conjugate multiplies with other signals, as those signals are orthogonal, they will have no contribution. So, finally, we will get this, and this is nothing but energy of the signal. So, when I multiply this with this, I get Es by m with minus. So, this will lead to minus Es by m. Similarly, using the same logic, I have minus Es by m from here. So, I have minus 2 Es by m, and using the same logic you can prove that this is nothing but this is also Es by m. So, finally, I get the answer is minus Es by m, and thus it completes the proof that simplex signals are not orthogonal signals. So, this brings us to the conclusion of this lecture. So, in this lecture we have started with orthogonal codes which are really important for power constrained channels like satellite channels, and we have seen 3 examples of orthogonal codes: FSK, pulse position modulation, then we have seen Walsh-Hadamard codes based modulation schemes, for example, which are used in CDMA systems. We have seen that all these modulation schemes ends up with having the same spectral efficiency and bandwidth requirement, and thus the only difference in all these varieties of orthogonal modulation schemes is their implementation. Rest the framework remains same, and we have seen interesting thing that the spectral efficiency of this modulation scheme decreases as m increases. This is really in contrast with what we have seen for m-com case. And finally, towards the end of the lecture, we have seen that you can also derive some other interesting signal sets from orthogonal signal sets. We can derive bi-orthogonal signal sets in which you just have the orthogonal and negative of those signals, that is bi-orthogonal. In simplex signal set, you just remove the mean of the orthogonal signal set. We have seen an interesting property of simplex signals, that simplex signals does not degrade performance, still they reduce the average symbol energy, and hence they are important. Of course, there might be some implementation issues with simplex signals. So, in the next lecture, we will look at differential modulation schemes. These differential modulation schemes are also important modulation schemes, particularly in the context of the channels where the phase response of the channel varies randomly and too fast. Thank you.